So thank you, Massimiliano. And thanks the organizers, of course, for setting up this very, very nice school. And for, of course, the invitation, the possibility to participate. So I'm gonna give some these 3 lectures on active matter, and possibly from a slightly different perspective, in the sense for what is usually done, in the sense that I will try to try to build an energetic discourse on active matter, in the sense of trying to understand what is the energy cost that is related to which is inherent to active matter. And so before doing that, and will be done mostly in the second lecture tomorrow and the day after tomorrow, today I would first like to maybe introduce some basic concepts, some that I hope are known to most of you. I will try to frame them in the sort of context of statistical physics and thermodynamics where possible. And then try to just introduce a couple of models that are like the kind of basic models that physicists use to describe some kind of active matter, and try to explain some basic features of that. And then tomorrow and the day after, try to build more, going back to the basics, and try to understand what is the thermodynamics, energetics going underneath these models. Okay, so let me start. I wanted to start with I have to, like, a disclaimer. I'm trying first to use some kind of possibly basic knowledge, or build on your kind of intuition for the first knowledge, and also maybe I will introduce or tacitly make some simplification, assumptions. If the expert feels that is at the limit of being, mistaken, you can also intervene and say, okay, no, maybe this is too much. Okay, so to start, I want to just use this quote that is probably, I don't know if it's taken from Wikipedia or from some basic description of some popular article on active matter. And this is a quote that says that kind of defines, broadly speaking, active matter as that kind of matter that consumes energy to create motion and forces and can self-organize into patterns. And there are some colors here because I wanted to try to go through this kind of this definition and try to frame it within the concepts that we have already heard about in this first week, and maybe add something more. And so when it says this definition that active matter consumes free energy, well, first of all, active matter is a collection of unit objects, can be on very broad different scales, and I will go to examples the next slide. But these are unit and objects that they transduce some form of free energy, so they take some free energy from some sort, can be from chemical type, can be a thermal type, thermal reservoir, so on and so forth. And for physicists, at least as it was born, and the prevalent idea nowadays is that these energies transduce and transform in the form of a specific form, which is essentially work, mechanical work. And this is what create essentially motion in the form of self-propulsion. So these units use this energy to propel themselves in space. Okay, so there is the prevalent idea of space or motion in space, and to exert forces. So these forces between active units, they are essentially of a form which is non-conservative because of the fact that we are transducing this free energy. There's a constant free energy input that is transformed into this mechanical work. This consumes means that this is done at a finite rate. So these are not quasi-static processes where you can do that for free. You can just borrow energy from a thermal bath, chemical bath, and then bring it back, so fluctuations. No, this is done at finite rate, this transformation, so there's a cost for that. So there is continuous dissipation. So we heard that, for example, in the context of chemical reaction networks. Francesco explained entropy, spent quite some time on entropy production. So this is a form of, this is free energy that is irreversibly lost, that we cannot use harness and use for good. So the point that is probably it's encoded in this word, which is self-organized, is related to the fact that active matter for physicists, from a physical point of view, I will stress this point from physicists and then transition maybe a little bit more to chemistry, possibly biochemistry, next 2 lectures. The point is that this energy input or free energy input is not on a global scale of the system, but is at this very scale of single units, okay? These are single units that move around, and they are forced at that microscopic level. So this will come clear for those that have no idea about active matter, but I hope that most of you have heard a little bit about that. That this means that we are not imposing any symmetry breaking at the level of the whole system. Like in traditional physics, statistical physics, non-equilibrium statistical physics, as it was done the previous century, we were looking at systems that were under the action of external gradient, like temperature gradients or electrical fields and pressure gradients. This is something that is imposed at the boundaries, okay? And if I do that, I break the spatial symmetry, right? So I do not the system self-organize, but I impose a privileged direction and for pattern formation, for example. And this is not what happens with active system, because I put in energy from the very microscopic scale. This energy can be randomly distributed according to the random direction of motion. And finally, the fact that we talk about patterns in space, this is the remarkable feature that you expect from active matter, and we have to look at we have to understand from a statistical point of view, patterns, statistical physics point of view, as phases and phase transitions that are not there at equilibrium. So at equilibrium, we are not dissipating any energy, so there's a constraint that is set by the local detail balance, and so from the Gibbs-Boltzmann factor, right? So high energy states, they will be populated according to the exponential of the beta energy, for example, in the canonical ensemble. So they will be much depleted. Well, once we start dissipating energy, so we are taking apart these constraints. So this means that we can populate states or phases that are not there, that cannot be stable at equilibrium. Okay, so these are probably the kind of main ingredients that lie behind this definition here. So before going more into the details, let me go and just took from a recent review paper about experiment or putative experiments that we can do even with microgravity, as we heard a little bit from Anupam also, on active matter. And this is like organized along a axis with different length scales from nanometers up to meters and more. And there is an arbitrary division into what we could call active matter and is biological and what is artificial or man-made. So, and what I described can be instantiation of what I described can be like molecular motors. I will discuss more about that tomorrow. Molecular motors, they are responsible for transport in the cell. They can activate essentially the driving units of motile microorganism of sperms, so cilia and flagella and so on. And this is still at the level of, if you want, these single units, they can work together to actuate this motion here. These guys there then can organize together to have some collective motion at the level of bacterial swarming, biofilms, and then we can transition from a world where thermal fluctuations are no longer relevant because at the macroscopic scale, so there will be some noise, but will be of some other kind, environmental noise. And we will have insects, herds of mammals, schools of fishes, and flock of birds and stuff like that, and human crowds. Okay, so at this kind of level, all these thermodynamic ideas that I gave you before, you see that are being kind of there. It's much harder to track them and to understand exactly where energy comes and goes. And the theme will be try to to see, essentially track this energy through scales in the next 2 lectures. But unfortunately, we will stop essentially at this point here. And on the other side, there are some examples of artificial systems, which is like artificial assays where you have like biopolymers, for example, cross-linked by active motors. And this is a good, essentially a good proxy for Janus particles. These are colloidal particles that I will spend time on that because they are good proxies to understand a little bit better of this swarming behavior. So these are particles that are driven by gradients. Okay, I will spend time tomorrow. And when you put many of them together, they end up in states of matter that you don't see at equilibrium, like gas-liquid transitions that are not possible at equilibrium. And then you can think about, you can run experiments at the macro scale with robots and stuff like that, okay? Where you can, where it's actually easier, it's actually very easy to understand how much energy you put into this kind of system because you just look at how much batteries you have used. Okay, these are just the broad ideas. And as I told you, I want to, and I will gonna go to the Blackboard soon. I just want to flash a couple of models that have been useful to physicists to understand how collective motion emerges in this active matter system, and try to get you a feeling of what's different from when you start dissipating energy and break detail balance. Okay, so there was one, possibly, or as far as I know, in physics, a lot of, I mean, the big attention that started to grow about active matter, everything began with this paper that became popular in the 90s by Witschek and his collaborators about the Witschek model. And the original idea was to try to understand how we can get collective motion flocking for units like animals, you know, that move. The original model was for example, like mammals moving on a plane, so on a two-dimensional setting. And the basic ingredients here is just that you have all these units. For example, you can think of these animals that they are just described by their position, so that can be their center of mass, and their direction, because they tend to move along their symmetry axis, if you want. Okay, and in this model is actually very simple. Okay, originally it was proposed as a discrete time model, so it was just implemented in simulation. So I will give you, and we will do some short calculation with a continuous time version of that. So the rule is essentially that all these units, they just move at a constant speed, okay? That is fixed from the outside because there's some internal energy that is provided by the metabolism to constantly move at that speed. And what they do, we impose by the outside that they tend to align. So in a certain neighborhood with a finite radius, for example, you look at the units around you, you look at their directions, you average more or less, possibly with some noise, okay? And then you just adjust your direction with the ones of your neighbors, and then you go on, and you make a step with that speed, and you repeat for all systems, okay? So this is I will go more into details in a moment. And this is more or less what you have. So if you are interested, like in this motion where you have many of these units, and you imagine that you can control how many of them you have in your system. So you run, for example, this simulation with periodic boundary conditions. So there's a finite surface defined. So there's a certain density, number of units per total area, and there is a noise intensity. So the noise that you put here on top of the aligning interactions, and you can tune this noise intensity. So it's called eta here, is intensity of this noise. You see that there's essentially you can identify some phases that you don't expect when the speed is set to 0, and we will see why you don't have them. So at high low density and high noise, everything is essentially disordered. You try to align to your neighbor, but there's too much noise, so and everyone ends up going in different direction. Then there's a transition to a state where essentially you create bands, okay? So these are in 2 dimension, that would be the strips that moves coherently in one direction in a sea of gas particles that move randomly, okay? This is what are called ordered bands. So if you lower the noise intensity or increase the density. And then you can end up, with some caveats, on an ordered, an homogeneous state where everyone is collectively moving. And this is something that could resemble like, a flock, birds that are flocking. So the whole system is covered by birds that are all moving with a certain direction in the same direction, okay? And then there's as I will tell you in a moment, there's a very simple scaling argument to understand how you can jump from here to there, which is based on mean free path and persistent length. Okay, so with that said, let's go back a bit more into the details. Is there any question for this very general part for now? Yes. Sorry, I have the noise. Sorry. There's no basis. So this is just an assumption, and the assumption is that, okay, this, you see, it's a model where you don't specify anything. I mean, you're not even saying at which scale these beasts are. This can be microorganism or can be animals. So everything, I mean, you just assume that there's some mechanism such that you tend to align to your neighbors, okay? We will see tomorrow, but I think you will not be there tomorrow, that for like microorganisms, this can be on the basis, for example, of hydrodynamics, because they are moving in a solvent fluid, they elicit a certain flow field, and this tends to, for example, align to neighbors, or there can be some chemotaxis or chemical signaling that it's at the basis of that. But for the moment, no, this I don't accept. Yeah. And yeah. So for the moment, we just assume that or something like that, and okay. So let me now write down like a continuous time version of the Witschek model that, as I said, originally was proposed as an algorithm. So there will be there's a vector R that describes is a 2-dimensional vector that describes the position at time t of each particle, and we said that particles are just moving at constant speed v0 along their orientation, okay? And this orientation vector, 2 dimensions, is gonna be a vector cos theta I, where theta you measure it with respect to any to a certain axis, okay? So we have these units, have this orientation, okay? And they are, this is I, this is J, and they are moving at constant speed along this orientation. And then, so you need, you can have an axis here, and you can measure this theta I with respect to this whatever axis, okay? Right? And then you have that the angles are changing. We said you want to align to a local environment. So one alignment rule that you can write down is that, okay, you just want the angle I to experience a force which is given by the sum sine of theta I, theta j of all the units that are around a certain your unit I, given a radius r. Okay, so these are all the units in a neighborhood. Let me call it, I don't know, it's a neighborhood of I. Okay, so this di is a neighborhood of I. And then you can add some noise. Okay, this noise, yes. There should be a dot here. Okay, it's a time derivative of r. Thanks. Okay. Okay, I have already phrased this model in a way that essentially I took this alignment from an energy function. So I sum over all spins, I sum over all neighborhoods that stay in the neighborhood of that spin of EI scalar product EJ. Okay, so this is minus sum over I, sum over j in the neighborhood of the cosine theta I minus theta j. Okay, and yes. Why I'm using this function? There's a particular reason for why I'm using this particular function. No, there's no particular reason in the sense that this model has been explored with an additive noise, has been explored with a noise where the noise you put not after the average but on the single angles, because you can say that of course a bird doesn't see exactly the direction of the other birds, but there's a certain noise, so you can put the noise there. There are a lot of variation, you don't get much different. I'm writing this model because this model has a clear, as I'm going to explain now, has a clear counterpart at equilibrium in statistical mechanics, and which is the XY model, okay? Because at V naught equal to 0, we have planar spins, okay, with an energy function given by that, okay? So I'm saying that this force now, it's just the derivative of this global energy. And so these are planar spins, this is the XY model. Okay, of statistical mechanics. And essentially I would say that after, like in StatMech class, after you do of interacting units, after you do the easy model in 1D, maybe you do the easy model in 1D plus strip, or in the 2D, and probably if you want to go further, you do the XY model, ideally. And so this means that V0 equal, if V naught equal to 0 means that I'm freezing everything, okay? All the spins are in a certain position and they can just align with local neighborhoods. And this is the classical XY model. And so there's a direct analogy, which is the order parameter, which is the magnetization, right? So the magnetization is that you sum over your, okay, let's say that where you have hand spins, you sum over the end spins, you make it an intensive quantity, so you divide it by the number of objects you have of your spin direction, okay? And okay, this is a vector. You can also, I mean, let's say that you take the define it by the scalar absolute value, which is gonna be between 0 and 1, okay? So if these guys, if these guys are all pointing in the same direction, this thing is gonna be 1. If they are all disorganized and looking in different direction, there's gonna be 0, right? Okay. And if, of course, this is at least, if you use, this is now a stochastic variable, the directed stochastic variable. Here is a stochastic variable that changes in time, so this m is a stochastic variable. Okay, so it will fluctuate. Okay, so even in a disordered system, is never going to be 0. Okay, there will be fluctuations around. So essentially, so I'm phrasing that in this within this context of the XY model, because in the XY, if you know the XY model, what you find is that in the XY model there's no long range order. So this means that in the XY model there will be m on average will be 0 always for any condition of your system. So imagine that this is a noise. Let's take it now to be like a noise due to the coupling with a thermal bath. So it's a big Gaussian, 0 mean, and correlation delta correlated in time, okay, the 2 kbt delta t prime delta ij. Okay, so I'm saying that the XY model, whatever temperature T finite, so different from 0, the magnetization is going to be 0. Okay? It's always going to be 0 for all T different from 0, essentially because, and I mean, my idea was to give it to you as an exercise, but we can set it up. Essentially, you have all these pins, and imagine that you have all these pins that are pointing in one direction. Okay, you're in 2D, so they are everywhere in 2D. Okay, and so on and so forth. And now imagine that with respect, and this would be magnetization 1, right? And then imagine that I devise the smallest perturbation that changes the least the energy. What should I do? Well, I can just change a little bit the direction of each angle such that, you know, this theta I minus theta j is very small. Okay? So the difference in the angles in the orientation is extremely small everywhere. Okay? And this is a tiny perturbation of your energy, okay? And what you can do is that you can let me write here. Well, you can write at the energy. Why I'm looking at the energy? I'm looking at the energy because at V naught equal to 0, we are at equilibrium. So the probability, equilibrium probability of a certain configuration, this is going to be given by, apart from partition function, e to the minus beta, the energy that depends on the full set of angles, right? So that's why I'm looking at the energy, because I have my constraint from local detail balance. Boltzmann factor determines the probability of states, macroscopic configurations, okay? So if I now go back to this idea that I put in a small perturbation, I get that my U now, perturbation of this kind, is going to be a constant, which is the one related to you set all the sum of you have n cos 0, which is 1. Okay, so you have this constant. This is relevant, and then you have a thing, which is the sum over I, then the j. Let me write it like that. Since now at v equal to 0, the domain, the local neighborhood is fixed. The topology of the system is fixed. There's a theta I minus theta j square plus higher orders. I've just expanded the cos, okay, 1 plus the argument squared over 2. Okay, and so you have this kind of energy. This is the small energy that you have in your system, and then you can go and calculate, try to calculate things. So you can say, okay, what's the correlation function? What's the magnetization now that I assume these very small fluctuations? And actually, what you can do an approximation. You can say, okay, I'm just interested in the long wavelength behavior. So I just zoom out. I don't look at the very small spins, but I look at the finite continuous distribution of spins. So I can approximate this guy here essentially with a gradient, because now they are continuously distributed in space, a gradient square, right? And this is just now essentially, for those who know what it is a Gaussian field theory. So if you go and calculate, for example, the magnetization, you get the magnetization is gonna be 1 plus what you have to calculate is the theta squared over 2 plus higher orders. This is a theta in one particular point. There is translation invariance, so you can pick any point. And so if you use the Boltzmann factor with this approximation, and that, you see that this guy is divergent, because in Fourier space, so in Fourier, these are just modes. In Fourier space, and you are in 2 dimensions, okay? This is diverges with the system size. So this is the log of the system size, okay? And so you said, okay, what's going on here? Well, it just means that the first assumption you made is inconsistent. You cannot just have a small fluctuations and expect to have a stable state, okay, at finite temperature. It does not exist. If you have a small fluctuations, these will destroy the long range order. So this small fluctuation will be always there whenever you have a continuous symmetry, which is spontaneously broken. So here you see this system is invariant under rotation. These are spins that can rotate. So if you have a magnetization 1, everyone is pointing in one direction, you have spontaneously broken the rotational symmetry. If you will always have this kind of spontaneous fluctuations. These are called Goldstone modes, essentially. And in different dimensions, in the space dimension, they can break, they can restore the complete symmetry that was broken. In this case, for the XY model in 2D, the fluctuations do that, okay? And that's why it's very, very surprising for a statistical physical point of view that whenever V0 is different from 0, as I showed you in the slide, you have these completely different patterns. You can have self-organization and motion, because that is magnetization different from 0, okay? So this for spins in two-dimensional system, this is, the fact that you cannot have long-range order, as this is a theorem with the name, which is the Mermin-Wagner theorem, okay? And that tells you that at finite temperature you cannot have long-range order. But it's just this is just due to the fact that you are constrained to populate some states according to the Boltzmann factor, because there's an energy that rules the system, and then small fluctuations they can destroy. They are essentially costless, okay? And they can destroy order. So it was a big surprise for physicists to see that once you switch on, you break this detailed Balmer condition, because you switch on this constant velocity. Now I'm going to tell you more in details why I'm breaking local detailed balance, or quantify that you are escaping all these ideas. Boltzmann factor is no longer constraining your phases, and then you can have fluctuation in energy. Doesn't care, because I don't care, because these are not their weights is no longer given by the Boltzmann factor. Okay, and yeah. It's a discrete symmetry. I'm saying, as I showed you here, this is just this is a continuous symmetry, so you can just steal them a little bit. These are called spin waves, so you can create that. In the Ising model, you have this discrete Z2 symmetry. Okay. Okay. but this is a little bit, if you are familiar with the Ising model in 1D, where you have the Landau argument, where you create the fluctuation with the least energy that you have, where you just flip all the spins from one point on. This is a very similar argument. You just look at the smallest energy fluctuation that you can create, and you see what happens to the system. Okay, and you get that you cannot have long-range order. As much as in this Ising model, in 1D you cannot have long-range order. Okay. So essentially, once you are escaped from the equilibrium constraint, you can ask yourself, okay, but once I start dissipating energy, it means that I can create whatever. I can have phases that are no longer there at equilibrium. Wait, you must break detail balance, but then you need some kinetics factors, some kinetic properties in your system in order to see the emerger of something new, okay? So we must go outside of equilibrium, but then we did some tweaking, some particular characteristics of our system in order to see something. So the idea in this system is that there is this very nice argument, which is very simple, and the idea is that now when V in the Witzek model, when V naught is different from 0, what can happen? Well, we know that there is this guy moving along his direction vector, okay? And let's assume, for example, that we are at very low density, okay? We are at very low densities, okay? So it's a kind of diffuse gas of self-propelled particles. And so if you are very low densities, it means that most of the time we are going almost straight apart from this angular noise, okay? So after some time, I will keep my direction for some time, but then, like, this is rotational Brownian motion, I will just deviate, and there will be a persistence length, no? There will be a particular length associated to this straight motion. Persistent length that I will call LP, and this persistence length will be, for a very dilute system, is not really at first order, is not really influenced by how many particles I have around. No, it's a property of a single particle. Then, of course, at higher density, I will start having more encounters, and then it will change. But at low density, it's gonna be like, well, what kind of typical quantities do I have for the single particle? Where I have a speed, and which is a length over time, so I have to multiply by a time, and so I will have to multiply by essentially the noise intensity. So I just want to keep, if I go back to the notation in the Witzek model, where there was essentially not, there was at the beginning there was not this parallel with the temperature of the thermal bath. So this noise was expressed as an eta, the intensity, you remember, eta square times, let's call it xi, okay? So I just I'm just rewriting this noise in terms of something which is of order 1, and then I took out the intensity of the noise, which was in the slide before. Sorry, I cannot keep the slides and writing on the blackboard. So this is the intensity that was in the phase diagram that I showed you before, okay? So this, if you see as the dimension of an inverse time, so the persistent length is V naught divided by the intensity of the noise. And so I want to go straight, and so keep my orientation till the moment where I find another particle, because This way, I can propagate information, okay? So loosely speaking, it's not the information as very quantitatively defined as before, but if I run straight and then at some point I meet my nearest neighbor, well, at that point the nearest neighbor will align with me, and so I will propagate this information of being straight, going straight through the system. So this means that this persistent length has to be compared with the mean free path. Mean free path, okay? L mean free path. The mean free path is defined as what? So the mean free path is the guy that is that direct, you know, I'm moving of a mean free path distance. The size of my particle is essentially related to the interaction radius, which is, let's call it R. So I'm sweeping in 2 dimensions, I'm sweeping this kind of surface, right? And in this surface, I must find at least one particle, okay? So there must be one particle in this surface, okay? And this defines the mean free path. Free path times R, this is the surface. If I multiply by the density, this in 2 dimensions is 1 over an area. This has to be of order 1, okay? And this is a definition of my mean free path. So this means that the mean free path is 1 over R rho, or at least it goes like that, okay? Apart from prefactors and stuff. So this means that when these two quantities, they are of the same order, it means that I have enough persistence to hit my nearest neighbor without changing my direction, right? So if you have a transition from a disordered gas to, let's say, what we saw was a traveling band, when these two quantities are of the same order. So it means when V naught eta square goes like 1 over R rho. And this gives you what I showed you before in the plot, so the fact that the critical noise at the critical, let's say the transition noise intensity, eta goes as the square root of rho. As you remember before, there was this plot with this behavior. Okay, these should all just at low densities because we set up this kind of argument for low density, but actually you see that it persists at very large density. So you see, we have to do some tuning on the kinetic parameters of our system. And so we have to go outside of equilibrium. We have to put in energy in order to break the constraint of lethal balance, but then we have to adjust the kinetics in order to allow for to get this transition, okay? So, but what does it mean exactly that we have to, this I need, let me delete that. Where is this breaking of detail balance here in this system? Well, imagine that maybe, of course, it might be obvious, but if you want to formalize it, well, imagine that we go back here to this equation and you look at this more carefully. Well, you see that this is just a sort of kinetic equation, right? In the sense that we're just imposing a constant velocity, while this other equation looks like a dynamical equation in the sense that it's like an overdamp diffusion equation for the angle. So there are the forces, the noise. Here that we don't see any forces, okay? So let's just rewrite it for a moment in a way that is more transparent, hopefully. So I can imagine that if this guy goes at constant speed, whatever it is, well, it's kind of exerting some forces on whatever, the substrate is if it's an animal, I mean the ground if it's an animal running, or the air if it's a bird moving. It's exerting some force, okay, in order to keep this velocity constant. So what can I write? Well, I will write it as well as a sort of overdamped equation where I'm just introducing this force, which is a kind of self-propulsive force that keeps the velocity constant. So keeps V naught different from 0, okay? And this is what you would expect when you write, physicists, if you write equation for a system of interacting particles, okay, you would write that this is overdamped, so you just have the velocity. I mean, there's a friction coefficient, if you want, set to 1 everywhere. It's a time scale, it's a global time scale that's set to 1, okay? And this friction force is balanced by the forces acting on the particle. So this is an internal force that keeps you moving, and then another one that tells you that whenever you encounter another particle, when a particle enters in your radius of interaction domain, well, there will be a variation in the energy, right? Because there was the energy written here before. The energy depends on the particle, how many particles you have in your neighborhood and how they are oriented, right? So it depends on the particle's position. Okay, so yeah. It had an R dependence even before. The U is defined as the sum over I, sum over J belonging to the neighborhood. So this belonging to the neighborhood means that there is a kind of Heaviside theta function that is 1 within the neighborhood and is 0 and depends on the particle position, okay? So it's a bit hidden here, but there's a minus, and then the cosine of theta I minus theta J, okay? So this is a function of both angles and position of the particles, right? So whenever a particle enter, I'm oriented like that, draw the others. If there is a particle that enters here, well, this guy, you have to update your energy, okay? And you have to count also for the interaction energy with the new particle that enters. So it's a function of space as well, okay? Right, yes. There's a factor 1/2, yeah, sorry. Yeah. So let me put it. Otherwise, I'm counting twice, okay. So I'm introducing this to make explicit the fact that I need this force to keep moving us straight constant speed, yeah. Yes, of course. There will be a delta function. The gradient of that is the gradient of a theta Heaviside, so there will be a delta function. Of course, if you want to do that specifically with this system, you run into trouble. What you can do, you can smooth your interaction, your domain around with something very, instead of having something like that, okay, you can just have something that smoothly interpolates with just some epsilon that you tend to you let to 0, okay? I'm just trying to apply some energetic thoughts, reasoning on a model that was not designed to do that at all, okay? That was just an algorithm that was set up to create some motion. But I want to unveil, to show where the energy input goes in, okay? And if you write it like that, there's no way you can understand it. Yeah.
So the reason why you use the same U is because the idea is that you apply the same derivative kind of in both equations. I mean, because physically you would expect a different potential.
Yeah, I'm just saying, imagine that you have, and you will be clearer with the model. that I have time, hopefully, to do today. Imagine that you write an equation for like colloidal particles that they move in space and they can also have an orientation. Okay, so what they will do translational Brownian motion plus there will be a force given by the interaction energy. So they will have this part. These are I'm just using the same energy. These are the same. These are particles with no hardcore interaction. These are just point-like particles. This is the minimal thing that I can do. I'm not adding anything on top of what I have already written before. Okay? There is an energy. I write the equation of motion taking like Hamiltonian equations plus a noise on the angles. Then I take an overdamped limit. You end up with this equation, okay? Without an F. If you don't put the F, they will not move at constant speed. So I put in another F in order to maintain the speed, okay? It's a kind of feedback mechanism to keep the speed constant. But that's the idea. You define an energy. The dynamics will evolve according to that energy, okay? And that is the same energy as before because these are point-like particles. So it's a very idealized system. Okay? So if you do that, now you can ask yourself, well, how much work is I have to do on this system to keep it in motion? Okay? So what I want to compute is the sum over all particles of velocity times this self-propulsion force on average. And of course, it will be a hard task because I have to solve for my dynamics and compute averages, and in general, I don't know what's the probability distributions. But what I can do, I can just, since everything is determined by this energy plus a non-conservative force, okay? If I wait long enough in my system with periodic boundary conditions, I will have that the time derivative of my energy will be 0 in a stationary state. Okay? And the time derivative of the mean is going to be the sum over all particles r dot I times u plus theta I theta u. Okay? And this I will have to average in the stationary state. Okay, but now I can use the equation of motion. And for those, who are familiar with that, I'm essentially trying to do some kind of stochastic thermodynamics, but not really. It's more like some stochastic energetics. And I'm not claiming here that, as you will see, that this has anything to do with the real energy that goes into the system, but it's just to understand how at that level we break detail balance, how we inject something in order to break this effective detail balance. Okay? So if you use the equation of motion, you can put in here and in there these expressions. Okay? So you can put that in there and this other here, and you end up, this part there will be an Fi, sorry, the other way around. Here I use the equation of motion for the gradient. Okay? And there I will use the F. So if you reshuffle things, you end up that we can isolate this quantity okay, you plug it on the you bring things on the other side, and then you get that since the r dot square will be a constant, you get a constant term minus something that for sure it's related to the angles, right? You can, it's not important that you see the details. They will be on my notes if you are interested. It's just the idea that counts here. So this is a gradient squared minus the second derivative, okay? And this is just because I used Ito formula to get rid of the noise, okay? It doesn't matter. The important thing here is that there is something that will be always there, will always be there, which is extensive. So it grows with the number of particles, with the system size. It will always be there unless we are at equilibrium. We are back to an XY model. So when V naught is equal to 0. And it's going to be positive. Well, you can also realize that if you go to very low temperatures is where you expect to find the pattern, right? To find the ordered motion. If you go at very high temperature, there will be too much noise. So let's go to very low temperature. If you go to the temperature essentially going to 0, well, this guy is gonna be awarded T, so going to 0, and that guy is the force that you can essentially, in a mean field fashion, you can evaluate as T goes to 0 as theta I of u mean squared, right? And there will be errors of some order in T. But since at very low temperature you expect to be magnetized, so m goes to 0, this is m is 1, this is essentially gonna be 0, because this is the average of the sign of theta I minus theta j. All the thetas are the same, so it's gonna be 0. So I'm saying that this quantity is gonna be very small, okay, at very low temperature with magnetization. So hand waving, I'm saying that what you have to do is that there will be something that depends on the configurations, very mildly, maybe at very low temperature. But the important thing is that you are constantly and extensively putting energy or a proxy for energy into your system, okay? Irrespective of what the exact configuration of angles will be, okay? And that's an important point, because we will see that this is a kind of fil rouge that you always have in this active system when we will go maybe tomorrow, the day after, to a more microscopic model of active system. This is not there. This kills with that exercise. This kills that at any temperature. Do it as an exercise. You do the integral of theta I e to the minus bu, integrating over all theta, for example, or the square of this. You see you have the same u here and there, so you can play with the partial integration. And you can see that this kills that at any temperature. Okay, so that was the trying to connect something well established and study from the point of view of configurations and phase transition to give you an idea of what's a sense of what should go on from the point of view of thermodynamics. But of course, as it was pointed out, I mean, these models, I mean, these are point-like particles. They are describing systems on a level that, I mean, we can try to be a bit more specific and trying to design models that are maybe addressing a more specific class of system for which it's easier to write down a faithful dynamical rules, and maybe also make a stronger connection with the real energetics. There was a line here. Okay. So okay. So let me just write the model. So I want to just introduce you the active Brownian particle model. Active Brownian particle model. And the idea is that we are scaling down. We want to describe, for example, we will see better tomorrow, like, for example, colloidal particles, self-driven colloidal particles that are so moving in a solvent. So they will then experience Brownian motion. So their coordinates wait a second, because maybe I wanted to tell you something more. No, 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 and no. Okay. So I'll give you example tomorrow, but imagine then now there are these particles. They are allowed, now we allow them to have some, to be some real particles, maybe some hardcore interactions. And if you want, there are people that like the Lennard-Jones potential, so we can put a Lennard-Jones potential here. If they are spherical, it can be more general, so this particle can be like elongated, so this U can be also a function of their orientation, if you want, because we still want something that has an orientation, where the orientation is just doing Brownian motion. So this is the same noise that I wrote before for the angle. Okay, so it's just describing Brownian rotation. But we have just decided, to not put in any explicit alignment. Okay, so then that's an important point. There is no explicit alignment rule in my system. So I'm just removing what was there in the Witschek model. Okay. I'm just allowing the orientation of these particles to randomly change due to thermal fluctuations. This d of r is a diffusion coefficient, okay, a rotational diffusion coefficient. And in space, there will be interaction, so potential forces of interactions. There will be another noise leading to Brownian translational rotation, Brownian motion, Brownian translational motion. Okay? And that would be a system at equilibrium, okay? And then, since these guys are self-propelled, I put the same thing as before, so the orientation vector times a constant speed. So let me specialize to a system where I have just, this guy is just a function of particle distances, okay? So I have a radial symmetric potential. Okay, so this means that I'm just describing spherical particles with an orientation. And they move along the symmetry axis. Yes? Sorry? So this is a vector, this is a unit vector, okay? This is a random eta I, so it was as before, maybe I forgot the j t prime. This is gonna be, so even there is a friction coefficient that is set to 1 everywhere. So this is gonna be 2 kb t delta t minus t prime delta I j, and this is a vector, so it's a scalar. You can read it as a matrix. So they're gonna be a unitary matrix here, okay? This is the standard Brownian motion translation. And this is maybe your less used, but it's just the rotational Brownian motion that we had used before. Okay? Okay. So let me see if I want to. 10 minutes. Okay. Yep. Okay. So okay, and this guy is similar. It's just that it's a scalar, but it's delta. It's finite. It's zero mean, delta correlated, and that's fine. Okay. So this model, imagine that you have just a radial. Let's use it the simplest example, radially symmetric. So these are spherical particles, and just assume that it is it's just a repulsive. Just repulsive. So we don't even take the Lennard-Jones. We just cut the Lennard-Jones when it goes below zero. Okay, it's just repulsive. So this system, and just assume for the moment that we are again in 2 dimensions. Okay, this is something that we will show maybe tomorrow. Can be realized where you have colloidal particles in a solvent and is tightly constrained in a plate. Yeah, who is there? You. As before, is the same the same unit vector that you measure with. You are in 2 dimensions, so you just need the one angle, and this angle is just doing rotation. So essentially, what you have is that. So if you look at the single particle, let's look just a single particle before. If you look at a single particle, you have that the angle is essentially is doing Brownian rotation. So the angle is there's a persistence time, if you want. So the angles are exponentially decorrelating because of this Brownian rotation, and with a time scale that is given by dr is the 1 over time. This is the angle. This is the theta. I don't see who is speaking. Okay. And so there's a similar phenomenology, at least if you consider the system at low density. It's a similar phenomenology to what we just said before for the Wittgenstein model, no? Because you have a persistent motion at low density. You don't. At low density, in this case, there is just rotational Brownian motion. So the persistent motion, after some time or some length, you convert from time to length with the V0. You lose this persistence, and then there is this length scale that you have to essentially compare with the mean free path of the system. So there is a similar kind of argument that you can have there from the kinetic point of view, that tells you that you can tune kinetic parameters in order to have some phases that you don't see at equilibrium. So at equilibrium would be V naught equal to 0. And indeed, you can find you can go to a phase where I will show maybe at the end, so I don't have to switch on the slides again. When you go to a coexistence of a liquid and a gas, so there will be a cluster of particles that are essentially embedded in a gas of randomly moving, low-density moving particles. Okay, so this is the so-called it's called the mobility-induced phase transition, because it's essentially due to the fact that I'm just thinking if I show you already something because it would be it's way easier to show one picture than 100 words. Okay. So that's what I was telling you. That's what I was telling you, that if you tune if you have that the persistent length is of the order of the mean free path, essentially you can create this kind of phase where you have a liquid inside a gas, so it's a high density. There is no way to break the spatial symmetry here in terms of the orientational symmetry here, because particle are spherical. You don't put in any kind of alignment interaction, so it's going to be impossible to have flocking. Okay, so there is no magnetization in the language of spins, but you can go to a system where there is a cluster, and essentially this is because when you tune the kinetics, you have broken detail balance due to the constant speed, and there is, from one of the original papers where this was measured in the experiments with colloidal particles, there is this figures that tells you essentially how it works. And it works because there is persistent motion. So whenever you have a kind of nucleation point for that liquid, so particles that are stuck together because they arrive there, well, if they arrive there, it will take some time, which is the rotational time due to rotational diffusion, to break this cluster, because this guy has to wait for noise to turn its nose out of the cluster, and at that point it will be able to escape. Okay, so yes, this is just random because at some point you can have particles that arrive there, but if they arrive there, that thing will stay there, because you are essentially breaking. The influx is larger than the outflux, and is larger in the sense that you have breaking detail balance, because there's a constant driving in one direction, which is the interior one. So how can you dismantle this kind of assembly block? Well, you have to wait for noise to reorient the particles. In that way, once they are reoriented because of the constant self-propulsion, at some point this cluster can break if you have the velocity is not large enough. If the density is not high enough, let's say, but if it's enough, okay, there will be other particles arriving and growing and giving this. Etienne, tell me if it's too simplified, but okay. Here there is no inertia in this model. It's just everything is overdamped, both the angle and the translation. Etienne. I don't know. I've worked with this model with inertia, but just to take the overdamped limit, but I don't know exactly what happens. Okay. This is a quite decent model. For example, we will see tomorrow for like self-propelled colloids. Regarding if you don't look at hydrodynamics interactions between mediated by the solvent, which can be true at relatively high densities, and in that case, for sure, everything is because of the scale. This is overdamped. Sorry, you are asking if I can have a model where I put... Yes. Like they have some memory kernel in the friction or something. Yes. It well, if it's an equilibrium model, I assume that you mean that there's detail balance. If there's detail balance and you put a memory in the friction kernel, you have to put a memory also in the correlation of the noise, right? Because of the fluctuation dissipation theorem. In that case, you can change the dynamics, but you cannot change the thermodynamics. So the states will be states by populated according to the Boltzmann factor. I don't understand. I'm saying that unless you put, I mean, if you put a constant speed, so you are essentially breaking detail balance, then you can tweak stuff, you can put memory and so on, and maybe you can have some phenomenology more. But if you just do what you told me, so just an equilibrium model where you just change the friction kernel and the kernel of the noise, this you can do. I mean, this is real Brownian motion. You know, if you do real Brownian motion in a fluid, it's not gonna be like that. I mean, if you go to short time scale, you will see that the diffusion will take seconds to kick in. But you don't change the configurations. You just change the kinetics. Unless you want to do something different that I don't understand. Yeah, maybe the in the original Witcher model, these are point-like particles. There's no repulsion. Yeah. Theta. Right. Sorry. Yeah. Sorry. Yeah. You. Sorry, it's you are right. The exponential would be for the orientation vector at first order. Yes. How do I implement like hard spheres? How do you implement hard spheres? And this is the point. That's what I wanted to finish the discussion first. So if you have hard spheres at equilibrium, in 2D, at finite temperature, you don't have a liquid gas transition. Okay, that's the striking thing. Difference with respect to the equilibrium case. Once you are in the active, you have this phase that is not there at equilibrium. Okay. Whatever, you can put just a repulsive, you can put whatever you want. You can also put soft spheres if you want, like an exponential potential or Gaussian potential, whatever you want. This is repulsion. I'm just saying that I don't want attraction. Liquid gas separation at equilibrium you get if you put attraction. Yes.
But if there is a high repulsion, like when you are trying to implement extruded vacuum,
Yeah.
they don't have to wait for the rotational noise. They can get some very high value of velocity in the opposite direction, and they can get far from each other.
If there's a radial potential, if they are in this configuration, I mean, imagine that it's an hard sphere. They cannot compenetrate. They will keep pushing in this way. I mean, if it's soft and the velocity is high enough, of course, they can just pass themselves. But imagine that the potential is hard enough. How can you break this cluster unless you rotate, or unless the translation of Brownian motion it's very, very large, extremely large? Maybe you are thinking about torques, right? A torque that can change. The torque with a potential, symmetric potential you cannot get. Okay. Okay, so this is taking a bit longer than what I wanted. Just maybe let me conclude, otherwise I don't have everything set for tomorrow. That, okay, you can, one thing that you can do with this model and with slightly more, with variation of these models, maybe some of them you have in mind or you tried yourself, I don't know, or you read about, well, you can imagine that at that scale, you are not interested in the dynamics of the of each particle, but you want to zoom out, and as we did for the XY model, when you look at spin waves, so a continuous, you can take a continuous vision of this kind of system. So it's a kind of hydrodynamic description, right? Hydrodynamic means I look at the local density. So in a small volume, I average the number of particles that I have. Or I look at the local orientation, so I average of a small volume, the orientation vector of my particles, okay? And I can write equations, okay, dynamical equations for these fields, okay? I will put in my notes if you want more. I have explanations for that. One thing that let me go back to for a second this mode. I mean, for this case, you can show that there is only one field that matters to actually describe this system, essentially because of all the assumptions we made here. And this field is just the density, so you can describe the dynamics, the phenomenology that I just showed you, sketched to you in a moment, of this model. I have with essentially an equation for the density, and well, in all this kind of system where, I mean, this is what is called scalar active matter, so I just need a scalar quantity, so the density, to describe them. Let me jump to the conclusion that you can rewrite on a certain time scale and long length scale, you can rewrite the dynamics, so the fluctuating dynamics that I showed you before, on long length and time scales in terms of an hydrodynamic equations for the density of particle at a certain point, at a certain time. So this will be my empirical density. It's defined as 1 over number of particles, sum over all particles in my system. I look at all of that particle that at time t are sitting at the position r, okay? This is a delta function. You can, hopefully there are no mathematicians here, you can make it smooth and then, okay, take a limit and so on. So this is a function well picked around the position r. So this is a fluctuating quantity because this guy, the coordinate of one particle is a stochastic variable. And so this thing essentially, well, is a density, so it must be conserved because the number of particles doesn't change, right? We cannot destroy particles here. So it's gonna be given by current field. So this is just a continuity equation. I've done nothing here. And this current, in general, gonna take this form. So there's gonna be a part, there's gonna be we will have it's a vector, this is a vector, and this is a noise. Okay, so this current here will have a contribution that comes from a gradient of a chemical potential. Okay, chemical potential is defined as derivative of the free energy of my system with respect to this density. There will be, and this is this is always there when you have even with an equilibrium system with a certain free energy. Activity will contribute a sort of a non-conservative force, F, okay? So it's going to be proportional to the V naught, to the velocity of the particle. So between these kind of thermodynamic forces, conservative and non-conservative, and the current, there will be a mobility coefficient, okay? That translates between currents and the forces, which will be in general a function of the density, okay? And there will be a noise, which is now a spatial noise. There will be a spatial noise with, so is a field. It's a function of R and T, which will be white in space and time. So it's gonna be something like 2 kb, let me write it like that. K times the delta of rho prime, T and T prime, and then I have my unit vector here. Okay. So this is just a translation from a particle-based model to field equations. So I don't want to track all particles. I just want to see what they do, what their density does. It turns out that with this model, you can reduce things to the density, essentially. You don't have to track also the orientation. If you are on time scale long enough such that the orientation just goes to a steady state faster than the density, okay? And this is the sort of equation that you end up with, okay? For the specific model, this free energy will have a contribution coming from the internal energy, which depends on the interaction energy that you put, and on the entropy. The entropy will be there for just for simple diffusion, no? That will this thing will just boil down to the Fick's law and to the diffusion equation. And the mobility also depends on what kind of interactions you put. And this force is just a coarse-grained version of what you had before, and depends on the self-propulsion. So just let me finish that, because now I'm just in a good position for tomorrow. And the point is that if I want to, what physicists do, and then they are used to that because they, in statistical physics, they in the last 10, 15, 20 years, they've heard a lot about stochastic thermodynamics, and so they want, given a dynamical description, which is stochastic description of some process, they would like to quantify the energetics of this system on the basis of how irreversible this description looks like. So what do I mean? I mean that, let me just take out this density here, which is the definition. Then, so this is a dynamical equation. You can imagine that this defines some sort, if you put it on a computer, you will have some evolution of the density, coarsening, formation of this cluster, for example, if you have the right parameters, and so on. And then imagine that you've recorded these noisy path trajectories, and then you just look at these backward in times. Okay, it will be probably look different, so you will see that there's a difference between the forward movie and the backward movie, okay? And this you can do, you redo your simulation starting from another initial condition, you will have another noise, so you will end up with a different path, okay? This means that if I record all that in a simulation, I will have a path, a probability, density, for all these instances of density at any point, at any time. It's a very thought experiment, actually. You cannot really do that. and currents. Okay? So you have, on a certain time span, you will have all these snapshots where at each point you have the density and the currents. And if you do a lot of these simulations, maybe you can extract from frequencies, you can extract a certain probability. Okay, and this is the probability of your movie. And then what you can do, you can just look at what happens. What's the probability to observe these movies when you look at backwards in time? So you just reverse time, you look at the movie backwards, and this will define a different path probability, okay, with the time reversed path probability that I will indicate just the arguments will be the same, and I just indicate that with an overbar. And if you have these two objects, you can look at how different they look like. So on average, so you can introduce essentially a relative entropy. So you have your probability as a function of this density, the path of density and currents, probability log the probability of density and currents. So this is the whole set of in the space and time, okay? And if I averaged over these two guys, right, that would be just the minus sign, that would be just the Shannon entropy associated with these path probabilities. But if I want to, Shannon entropy, I mean, if I want to, is a relative entropy with respect to a flat distribution. So if I want now to compare with what I said is the backward movie, so it's the one with the probability where I see things in time reversed, okay? I take the average of the log ratio between forward and backward path probabilities. Okay, this is a relative entropy. It's called to the Kullback-Leibler divergence. It tells you how different two probabilities are. It's not a distance between, let's call it P and the overhead. If I want to do that in math, a time reversal here would be okay. Well, just take the path probability associated to these dynamics and just reverse time. Okay. If I reverse time, this means that dt rho is mapped into minus dt rho, and you see that a current has the same parity under time reversal or time derivative. Okay. Because space, of course, doesn't change under time derivative, so this must change sign if that changes sign. So I map J into minus J. Okay? If you do that, and this I conclude, and I will come back to this tomorrow. You end up with a DKL, which is beta minus delta F plus integral in space and in time of the force times the current average. Okay? Okay, so why we would like to use this definition? Well, because whenever you have a system whose dynamics describes, as it was said by Francesco, for example, all the non-equilibrium degrees of freedom are explicitly described by these dynamics, well, in that case, this Kullback-Leibler divergence is related to the thermodynamic entropy production, okay? So to the quantity of free energy that is dissipated up to a factor temperature, okay? So in that case, that would be the real fraction of free energy that is dissipated by my system. But in this case, well, already you see that already I told you that you need some kind of simplification to go from the particle-based description to the field description. You understand very well that the particle-based in the first place was a model that was just reproducing phenomenology, so it's very coarse. Doesn't tell you, for example, where the energy comes from to create the self-propulsion. So this guy will surely be less than the dissipated free energy or dissipated entropy of my the real microscopic dynamics, okay? But still, since this is relatively easy to access from a description that phenomenologically captures what happens, well, we can, as physicists, we can have the hope that it tells us also about the underlying energetics, okay? And you should be skeptical now, very skeptical, and we will see the next day, tomorrow, how it goes, okay? Yes? Yeah. Depends only on? No, wait a second. So just, you gave me this opportunity. So the path probability of rho and J, this guy is a Gaussian field. So the path probability for sequence of noise in space and time will be a Gaussian, okay? So if I just rewrite this Gaussian in terms of these new variables, okay, of these new variables, rho and J, you see, so you see J is equal to that plus the noise. So this thing is gonna be something like e to the minus integral over time, integral over space of J minus that thing here, okay? That's called, I can call it capital J of rho. Okay, so all this guy is capital J of rho. Okay, and then the variance is gonna be given by the variance of the noise that was written here, but I deleted. So it's gonna be like 4 kBT mobility, and there was nothing else, I guess. Okay. And then you need that constraint in order to enforce that part of the equation, right? So you need that at any time dt rho plus divergence of J is equal to 0. So it's a product of this Gaussian part with this delta that tells you, well, continuity equation must be enforced, okay? And so you see it's a function of J and on rho. Yeah, sorry for being late, 10 minutes late.